Imagine being able to visualize current flow from a young age. We are the Resistance. My name is Asim Ghazi and I'm the team lead. This is Jacqueline Zabranik, our document manager, Gurman Singh, our schedule manager, Brett Gable, our software lead, and Mohibus Chaudhry, our hardware lead.
At the beginning of last semester, we found that the first time we'd been introduced to electrical circuits was our junior year in high school, and also that none of us started out as electrical engineering majors. Over the past few years, we've come to enjoy the field of electrical engineering and would like to share it with younger students, thus coming up with our project, Build a Circuit. The goal of Build a Circuit is to introduce basic electrical circuit concepts to elementary school and middle school age students through the visualization of current in an interactive way.
So how do we accomplish this project? Well, we have 5 acrylic blocks that represent different circuit elements, such as a resistor, a diode, a light bulb. And to show current, we have implemented RGB LED strips that show the current's magnitude and direction as well. Furthermore, to ensure safety, we have hidden all the circuitry and wires underneath the circuit so the user does not have access to them. Furthermore, in order to test the project and collect data, we had to get approval from the IRB, which is the Institutional Review Board of UT Dallas, to ensure ethical standards. Furthermore, we'll be providing documentation that shows the children how to actually build a circuit, like a user's manual.
The software process for our design begins when the user presses the simulate button. The Raspberry Pi will then read in the switch inputs and translate that into a netlist. This netlist is then simulated by NuCap, and the current information is extracted and sent to an Arduino. The Arduino then drives the LEDs accordingly, displaying nothing if it's an open circuit, flashing red if there's a short circuit, or showing the current, as you can see, if the circuit is complete. And we have special behavior for the LED and the light bulb block. And the block diagram shows how all of our hardware communicates.
Now, how do we bring this project to life? Well, we have a design space with 16 nodes with 23 slots. The user will place these acrylic blocks into the slots, and after the simulation button is pressed, the current flow will be shown, as you can see in the video here. But what's interesting about our project is that our project shows the current direction as well as the magnitude, and we have a separate speed for the current flow as well.
So now that our project is complete, how do we effectively evaluate our product? Well, we've broken that down into 2 categories. The first deals with our project's instructiveness. Do the results from the user-created circuit model those of what we expect from the equivalent physical circuit? And on top of that, viewed from above, does a completed circuit with blocks in place look like a circuit schematic? The second category deals with user engagement. We've done our best to ensure our product is aesthetically pleasing enough to hook the user. And now once the user is hooked, we also want to ensure that they enjoy experimenting with the toy. And that's where these survey results come into play. 2 highlights from this table: 70% of users come in to the 10-minute interactive session with no familiarity whatsoever with circuitry. Yet 85% leave with a good qualitative understanding of what each circuit element does. The second highlight to take away: we allowed users to choose all that applied from 4 different categories: fun, boring, interesting, exciting, and absolutely 0.0% felt our project was boring. Our project's name is Build a Circuit. Thank you for your time.
All right.
And then we'll open it. At this point, so data retrieval is still in progress. So we went to the Perot Museum, actually. We were invited to go to the Perot Museum, and 18 users agreed to actually fill out the survey and go through the whole IRB approval process.
What's the age range that you were targeting here?
This is for ages 5 through 17.
How do you compare this to existing educational tools?
Sure. Snap circuits is a really good example. So snap circuits is where you put the blocks in place, right? You got a battery block, and you put these other blocks in place, and then the fan turns on. But what we realized was missing from those products is that it still seems magical for the student, right? They look and they put all the blocks and they turn on the fan, but do they know that there's current flow through? That's why the fan turned on? So that's what we want to show through our project, is that there is actual current flow through. And as you can see in the GIF above, there are actually light bulb blocks that are turned on, so the student understands that if there's current flow through the light bulb, then it turns on. But actually, if we connect a circuit that doesn't allow current flow through a certain light bulb, it will not turn on. For example, if we put a light bulb in parallel with a wire, right? All the current will flow through that wire. So the student will then understand, oh my gosh, if there's no current flow through a component, it's not going to work.
What is your circuit? I mean, how, is it physically a piece of plastic or?
So we're using these acrylic blocks that are encoded with paint on the bottom. So
Yeah.
actually, these acrylic blocks have no circuit
Okay.
circuit element inside or anything, nothing embedded in comparison to snap circuits and our competitors, so to speak. There's nothing embedded in these blocks. It's actually going to be placed in the board. The sensors read that encoding, right? Send that information, of course, to our Raspberry Pi. The Raspberry Pi does the decoding, writes a netlist file. The netlist file gets simulated through NuCap, which is similar to PSpice. And then the current values are outputted, and then the LEDs turn on accordingly by instruction from the Arduino.
One last question.
They can build anything they want, or?
Anything they want. So we focused on DC circuits specifically because this age range is before university level, right? We're focusing on that age range just to introduce these students. So we've allowed them 5 block choices: a wire, resistor, diode, LED, and light bulb. And our board will actually pick up the direction of the diode and LED. So if they put the diode in the wrong direction, they'll understand. And that's what I meant by the qualitative understanding. You can imagine 6 and 7-year-olds at the Perot Museum left with an understanding that if I put the diode in the wrong direction, that's why my circuit's not working. So they understood that the current only flowed in one direction. That's the qualitative understanding we spoke of.
And your magnitude you're talking about is just increased light density?
Actually, it's the speed. I hope it's easy to see here, but you can see in that first loop right next to the battery. The battery's on the left. It's a little hard to see on the slide, but the battery's on the left. You'll see that the loop closest to the battery has the highest current magnitude. So you'll see the LEDs actually in green flow faster than those of the other loops. So for the second loop, we purposefully created the circuit to show there's a slower current, so lesser magnitude, a medium one in the middle, and then a really slow loop at the very end.
And you have set it up at the poster session.
Exactly. So yes,
it will
please
be
come by.
on display in the afternoon.
So if you all want to build a circuit, come to our poster session.
Okay.
About safety, the safety of the circuit.
Safety.
Did you have to do some norms, some prescription on how to design the circuit?
Yeah, one of the biggest things was the blocks themselves, right? We had to ensure that they weren't a choke hazard, so they actually meet that
About the
standard.
electricity?
The electricity, everything is hidden from the user, nailed and all closed up. The sensors under sheets of acrylic that are also nailed in, so everything is pretty robust against any users trying to figure out and trying to mess with any circuitry.
All right. Let's thank the team.